thanks for inviting me to talk. And like Philip said, I'm going to talk about primes in arithmetic progressions. The basic question is, if we look at the sequence A plus Q, A plus 2Q, then how many primes are in the sequence? And if A and Q share a prime factor, that's of course a very boring question. There can only be at most one prime. So really we are thinking about A and Q being coprime. And if A and Q are coprime, and we ask how many primes are there up to X, which are in the residue class A mod Q, then it's known that this is asymptotically equal to the number of primes overall divided by phi of Q. And because the number of coprime residue classes is phi of Q, that means that the primes are equally likely to be in any of the coprime residue classes mod Q. So that's why we say that the primes are equidistributed in arithmetic progressions. But if we want to better understand the number of primes in a progression, then of course we want to know something about the error term for this. So we're asking what's the difference between the number of primes in a progression and the expected number of primes. And for that, we can use the Siegel-Waldfried theorem, which says that the error term is x over e to a constant times log x to 1/2. But that's only useful for q very small. So q needs to be less than or equal to a power of log x. And that's not very helpful if q is large. But just like the Riemann hypothesis gives better error terms for primes, if we can assume the generalized Riemann hypothesis, we get better error terms for primes in arithmetic progressions. So with the generalized Riemann hypothesis, we know that the error is x to 1/2 times log x squared. And because the main term is x over log x times phi of q, if the q is a bit less than x to 1/2, then the main term is bigger than the x to 1/2 log x squared. So this is a good estimate if the modulus q is a bit smaller than x to 1/2, where x is the length of the sequence. Now, the unfortunate thing is, if we want to prove anything unconditional, then assuming the generalized Riemann hypothesis is not very helpful. So, but fortunately, as a replacement for that, we have the Bombieri-Vinogradov theorem. So what the Bombieri-Vinogradov theorem says is, if we don't just look at one modulus, but at all the moduli up to x to 1/2 over log x to some power, and look at all the residue classes A mod q, which are coprime, then the sum of the error terms is bounded by x over log x to the A. And because we are looking at a bit less than x to 1/2 moduli, and the upper bound is x over log x to the A, that tells us that, at least on average, we have the error term predicted by the generalized Riemann hypothesis. And this is a really, really useful result in sieve theory. So in sieve theory, if we want to understand the properties of primes, it's often really important to understand the properties of primes in progressions. And this upper bound in the Bombieri-Vinogradov theorem is used a lot. And for example, in Zhang's proof of the almost prime version of the Goldberg conjecture, or in proofs of bounding gaps between primes. Now, the x to 1/2, it's predicted by the Halberstam conjecture that we can improve this from x to 1/2 to 1 minus epsilon, so that the average error term is very, very small. But unfortunately, this 1/2, which is sometimes called the exponent of distribution of the primes, hasn't been improved since 1965. So we think we can replace the half by any number up to 1 minus epsilon, but we are stuck at the half. And one of the reasons this is unfortunate is related to a twin prime conjecture. So twin prime conjecture, of course, says there's infinitely many primes, p and p plus 2. But a weaker statement would be the question if there's infinitely many pairs of primes, p and p plus h. And until 2030, not even that was known. But what was known is that if the primes have an exponent of distribution larger than 1/2, so if we could improve the Bombieri-Vinogradov theorem, then Goldstein, Biltz, and Yildirim showed that there is some gap h between the primes that appears infinitely often. So at least with a large exponent of distribution, it was known that such an h exists. And that was a big breakthrough in itself, but unfortunately we were stuck at getting an unconditional result until Yi and Sun made his breakthrough in 2013. And the way he got around the issue of not being able to improve the exponent of distribution in the Bombay-Vinograd theorem was to look at not all moduli, but just the ones that are smooth. So instead of thinking about all the moduli Q, he just looked at moduli Q, which have lots and lots of small prime factors. And this extra flexibility allows us to prove better equidistribution estimates. So if we only look at smooth moduli, then the average error term he showed is less than x to 1/2 minus 1/584. And this statement here, he was able to show on the one hand that we get this equidistribution estimate for smooth moduli, and on the other hand, that this weakened version of the Bombay-Vinograd theorem is still enough to prove boundary gaps between primes. So to show that there's some age between 2 and 7 million, which is infinitely often a prime gap. So this statement is weaker than Bombay-Vinograd in two ways. So on the one hand, we only look at smooth moduli, and on the other hand, we're looking at a fixed residue class. So instead of looking at a maximum over all the residue classes A, we're just looking at one that's fixed. But the upper bound is not allowed to depend on A. So there's lots of results out there which allow the upper bound to depend on A, for example, by Maynard, Lichtman, Bascardi. But if we want to apply it to the results on boundary gaps between primes, we need to have an upper bound that's independent of the fixed residue class A. So this is the type of result we are interested in this talk. So Zhang used this to show gaps between H1 have a gap, between two primes have a gap that appears infinitely often. And Maynard and Dow independently generalized this to gaps between n+1 primes. So if you look at gaps between n+1 primes, then there's also a gap length that appears infinitely often. And the better the exponent of distribution for primes with smooth moduli, in arithmetic progressions with smooth moduli, the stronger are the upper bounds on HM that we get. So Zhang had an exponent of distribution 1/2 plus 1/524, and Polymath improved this to 1/2 plus 7/300, and we recently improved this one to 1/2 plus 1/40. So if you look at primes with smooth moduli, so all the if you look at primes in arithmetic progressions with smooth moduli, so all the factors are less than let's say x to the delta, then the average size of the error term for the difference between the number of primes in the arithmetic progression and the expected number of primes is bounded by x to 1/2 minus 1/40. So what I want to talk about in this talk are two things. On the one hand, I want to talk about why there's this link between equidistribution estimates and boundary gaps between primes. So I will summarize the work of Children, Zhang, Maynard and Dow, and so on. And then after that, in the end, I want to talk about how we get from 1/2 plus 7/300, which is the result of Polymath to 1/2 plus 1/40. And the input here is an amendment of the Q van der Corput method. So I'm going to talk a little bit about what the Q van der Corput method is and how we can improve it a little bit. Okay, but first I'm going to motivate our interest in smooth moduli a bit more by talking about the proof of boundary gaps between primes. And it turns out bounding the infimum of the gaps between n+1 primes is very closely linked to the Hadley-Littlewood conjecture. So if we look at the tuple h1 up to hk, we ask, is it the case that for infinite many shifts n, all the entries of n plus h1 up to n plus hk are prime? And for example, if h1 up to hk is the tuple 0, 2, that would be the twin prime conjecture. If we have the tuple 0, 2, 4, then one entry of n plus 2, n plus 4 is always divisible by 3. So clearly it can't be all prime infinitely often. So what we're interested in is tuples h1 up to hk, where for each prime p, there's one residue class mod p that's missing. And for those tuples, the Hadley-Littlewood conjecture says that there's infinitely many n for which all entries of n plus h1 up to n plus hk are prime. Now, unfortunately, the Hadley-Littlewood conjecture is open for any k greater equal to 2, so that's not very helpful. So really, we're interested in a statement that's a bit weaker. So instead of thinking about all entries of a tuple being prime, we're asking for, let's say, at least j of the entries to be prime. So we say the weak Dixon-Hardy-Littlewood conjecture is the conjecture that if h1 up to hk is admissible, then for infinitely many integers n, at least j of those k entries are prime. And if we can show that such a statement is true for tuples with k entries, and that there's n plus 1 primes, that means infinitely often n plus h1 and to n plus hk has n plus 1 prime entries, and the difference between the smallest and the largest is bounded by hk minus h1. So that gives an upper bound on the lim-inf of the prime gaps of hk minus h1. So if we say capital H of k is the minimal diameter of an admissible k tuple, then if the weak Dixon-Hardy-Littlewood conjecture for k and n plus 1 is true, the infimum limit of Pn plus m minus Pn is bounded by the minimal diameter of admissible k tuples. Okay, so this is the kind of statement we want to prove, and for that purpose, Goldstein, Binz, and Yildirim developed the GBY method. So this works as follows. The starting point is this expression n of x. We have a sum over the prime indicator function applied to n plus h1 up to n plus hk, and we subtract m, and then we weight it by a weight function. So let's think about what happens if n of x is greater than 0. In that case, because the weight function is non-negative, one of those differences needs to be positive, and that means for some choice of n between x and 2x, there must be at least n plus 1 prime entries. So at least n plus 1 values n plus h1 up to n plus hk are prime. And that's exactly the kind of statement we want to prove. So the idea is we have this expression n of x, and we want to show it's greater than 0 for large x. Now that's, of course, much easier said than done, because this is not going to be true for, let's say, most choices of weight function, or at least we're not going to be able to show it. So the big question is, what's a good choice of nu here? And Cheap and Y themselves, they constructed a weight function which was good enough to show this when the exponent of distribution of the primes of the primes was bigger than 1/2, but it wasn't good enough when it was less than 1/2, which is the current state of the Bombera-Vinogrado theorem. And so we're asking what's the best choice of weight function nu here? And to understand this, it's good to rearrange the question nx greater 0 just a little bit. So this is equivalent to the sum of the nu n weighted by the prime indicator functions n plus hi over the sum of the nu n being greater than m. And so what we want to be able to do is to choose a weight function nu so that this ratio here is large. Now in the denominator, we are summing over all values n. And in the numerator, we are summing only over those n where n plus hi is prime. So if we want to make the ratio large, this is a problem, unless nu n itself is only large if n plus hi is a prime. Now we can't quite make it so that it's only large at primes, so we think about primes and products of few primes. So we want to find the nu n, which is only large when n plus hi is a prime or a product of few primes. And for that purpose, Maynard and Dow came up with the Maynard-Dow Sif weights, and they look as follows. So first, we have a function lambda f, which is a convolution of 1 and nu d times f log x of d, where f is some smooth, compactly supported function. And in Sif theory, it's known that this function can be viewed as a smoothed out version of an indicator function for primes and products of few primes. So to make sure that nu is only large when we have a prime or a product of few primes, we take each of the n plus hi and we apply lambda to those. And then we are allowed to take some linear combination, and then we are squaring it to make sure that nu is non-negative. And this is a really flexible choice of Sif weight, because for each of the n plus hi, the smooth function fji can be chosen differently, and then we have this coefficient cj, which can be chosen in any way we want. This is a very flexible choice of the Sif weights, and it turns out that for this choice, the n tilde of x is asymptotically equal to this complicated expression, which is not so important right now. It's just important thing to observe is that if we choose the weights like that, we can compute n tilde. And so we have reduced the problem of showing an upper bound on gaps between primes to solving an optimization problem. So as a very brief overview, if the weak Dixon-Hardy-Littlewood conjecture for k and m plus 1 is true, then that means that the lim-inf of gaps between m plus 1 primes is bounded by the length of the shortest admissible k-tuple. And to prove the weak Dixon-Hardy-Littlewood conjecture, we want to use the GPY method and show that n of x, which depends on k and m, is greater than 0. And to show this, we use the Maynard-Tower sieve weights. And with those, it can be shown that n of x is greater than 0 if this ratio here is greater than m. So that's the optimization problem. And this is a difficult optimization problem, but this gives a concrete plan to proving upper bounds on the lim-inf. But you will notice that I said that the purpose of this talk is to show, to highlight the link between equidistribution estimates for smooth moduli and bounding gaps between primes. And I haven't actually mentioned equidistribution estimates yet at all. So something is missing. And what's missing is that it's not actually true, or at least known, that n tilde x is always asymptotically equal to this expression. We need to show that n tilde x is something, like stated here. And to do so, we need to use the equidistribution estimates. So the purpose of the equidistribution estimates for smooth moduli is that it determines the domain of our optimization problem. An optimization problem needs a domain, and the equidistribution estimates tell us which choices of FJI are suitable to be able to compute n tilde of x at all. Because this ratio is meaningless if we can't link it to our original problem. Okay, so why is this the case that the equidistribution estimates are important here? Well, if we want to compute n tilde, that's a ratio of a sum of nu n times prime indicator functions over a sum of nu n. The sum of nu n itself is a bit easier to compute, so the hard part is computing nu n weighted by prime indicator functions. And if we substitute in the Maynard-Tower sieve weights and just rearrange a little bit, not doing anything exciting, just by rearranging, we get this expression here. And it's a sum over some di, and then there's a coefficient, and then here is a sum of prime indicator functions. So that's where arithmetic progressions appear for the primes. So if we take this expression for nu n times the prime indicator function and want to estimate it, we replace the sum of number of primes in an arithmetic progression by the expected number of primes, which is x over log x times phi of d1 dot dk dash, and then we try to bound the error term. And the error term looks like this, and that's exactly the kind of equidistribution estimate I talked about at the start of the talk. So we get a nice asymptotic for this expression, as long as we can get an upper bound on this sum of error terms of the number of primes in arithmetic progressions mod d1 dot dk dash. Now, we have a small problem. I said we want an upper bound here, but I didn't actually give any restrictions on the di. If we just arbitrarily sum over all possible di's, we're going to get a huge number. So somehow we need to restrict what di's we are summing over. So we take a look here at the coefficients, and we notice that for each di, we are applying FJI log x of di to it. And so a di is only going to contribute if log x di is in the support of FJI. Otherwise, we're just getting 0. So the way we restrict the sum is that we're only looking at those di for which log to base x of di is in the support of FJI. And that gives us a way of applying known equidistribution estimates. So for example, if we look at log x di support FJI and we have the restriction that the upper bounds in all the supports summed up is bounded by 1 over 4, then the sum of the log x di is bounded by 1 over 4, and the product of the di times di dash is bounded by x to 1/2 minus epsilon. And so here, in this case, we can apply the Bombero-Vinograd theorem. So that's one way to approach it. And of course, our hope is that if we have a larger range for the supports, so a larger available space of functions FGI, then we're going to get better results in the optimization problem. So instead of having the 1/4 from the Bombiara-Vinograda theorem here, we would like something larger than 1/4. And this is where we can use equidistribution estimates for smooth modeling, because instead of 1/4, let's say we use 1/4 plus omega. The problem is then we don't have the Bombiara-Vinograda theorem, but we can fix this by restricting the individual supports of the FGI to 0, delta, because then the log XDI is bounded by delta, and that means each of the DI is bounded by x with delta, and if each factor DI is bounded by x with delta, that means all the prime factors are less than x with delta. So we can extend the support of the functions if we introduce the extra condition that the individual supports are contained in 0 delta. So there's basically two options. We can either not restricted supports and use Bombiara-Vinograda, or have restricted supports and use equidistribution estimates for smooth modeling. And which one works better depends on the problem. So it turns out if we only think about gaps between two primes, it's today known that it's with the Main-Tarsif, it's better to use Bombiara-Vinograda. So it wasn't possible to use Bombiara-Vinograda with GPY weights, but with the Main-Tarsif weights, we get the best result by using Bombiara-Vinograda for gaps between two primes, and then for 3 and more primes, it's better to use smooth modeling, because the restricted support for the individual functions is less of a trade-off than the larger support overall. Okay, and the concrete result is that if the primes have exponential distribution 1/2 plus 2 omega, then N tilde has a lower bound 1/4 plus omega times log k. And if we want to get an upper bound on gaps within m plus 1 primes, then we need N tilde to be larger than m. And so we need the k to be larger than e to the m over 1/4 plus omega. And the upper bound on Hm is the length of the shortest visible tuple of length k, which is bounded by k log k. So overall, this gives an upper bound of e to the m over 1/4 plus omega for gaps between m plus 1 primes. And here the 1/4 plus omega, so that 1/2 plus 2 omega is the exponent of distribution of smooth modeling. So if you use the Polymath result of 1/2 plus 7/300, that gives e to the 3.822m. And Baker and Erwin, they improved this by replacing the prime indicator function by a suitable minor run using Hammond-Siff, and they improved it to 3.815m this way. And if we use the exponent of distribution 1/2 plus 1/40, we get e to the 3.81m with just the method of Polymath, and combining it with Baker and Erwin's result, we get 3.8075m. So a small improvement in the exponent. Of course, we think that actual bound on HM is much, much smaller than that. And we can also improve upper bounds on H2, H3, and so on. And I have put here a small table of improvements. And Sutherland was kind enough to compute the length of concrete length of admissible K tuple here for us. And you can see for H2, the actual size, the known size was 398,130 before, and now it's improved by 2,000. So a very small improvement, but better than nothing. Okay, so this is an overview of the proof of boundary gaps between primes and how equidistribution estimates fit in. And now I want to talk about how we actually prove exponents of distributions for smooth modeling. And I don't have enough time to go over the full proof because it's a very long proof. So I want to focus on the role of the Q van der Corput method in the proof. And so it turns out that if we want to prove an exponent of distribution for the primes to smooth modeling, we need to work with exponential sums. So they play a really key role. So let me first talk about how exponential sums are used in the proof. So we are defining EQ of Fn to be e to the 2 per I Fn over Q if Fn is an integer, and if Fn is, let's say, a ratio or something, then we say Fn overline is an integer which is congruent to fn mod q. So either way, here we have an integer, and the EQ of fn is e to the 2 pi, and the suitable residue class mod q over q. And an exponential sum is a sum of EQ f of n. And there's lots and lots and lots of work out there on bounding exponential sums, which I can't possibly do justice in a few minutes, so I'm not going to try. And I'm just going to highlight one famous result of Weil that says that if we just look at complete exponential sums, and we have a modulus p, which is a prime, and the phase Pn over Qn, where P and Q are suitable polynomials, then this complete exponential sum is bounded by square root of b. And the reason I mentioned this result is because it highlights one typical property of bounds in exponential sums, and that's that the upper bound gets worse the larger the modulus p here is. So smaller moduli for the exponentials give better upper bounds. And so the idea of the Q van der Corput method is that we don't like large moduli in the exponential sums, and we want to reduce the size of the modulus. So the standard van der Corput method, which is maybe known a lot better, is that we have an exponential sums, and the phase is a polynomial, and we are trying to prove bounds on the exponential sum by using the Cauchy-Schwarz inequality to reduce the degree of the polynomial. And in the Q van der Corput method, the idea is very similar, but instead of reducing the degree of a polynomial, we're reducing the size of a modulus. So let me show you how it works. So let's say we have an exponential sum, and we have a modulus m times d, and we want to reduce the size of the modulus by getting rid of the little d here. Then the way we do this is we fix the residue class of n mod d inside the sum, and outside we're summing over all the residue classes. So that's just triangle inequality. And then we apply the Chinese remainder theorem to replace emd f of n by ed fn over m times em fn over d. And here the n is in a fixed residue class mod d, and so that means fn over m is fixed mod d, and so this factor here is a constant, and we can just remove it. So removing it, we have a sum of em fn over d. And at first it looks like we've already gotten rid of the modulus because it's not here anymore, it's em instead of emd, but we still have the d inside here. So not really anything has happened yet. There's still an over d. So in order to get actually rid of this over d, what we do is we apply the Cauchy-Schwarz inequality. So if we apply the Cauchy-Schwarz inequality, we instead get the sum, a square of the sum of em f and d on the inside, and expanding that we have em f and tilde minus fn over d. And if we have, say, n tilde equal to n, then we immediately see that we're in trouble. So if n tilde is equal to n, then fn tilde minus fn is 0, and then we get lots and lots of 1s, and that gives us a diagonal term of d to 1/2 times n to 1/2. So we get this large diagonal term, but then for the often diagonal terms where n is not equal to n tilde, we hope that we can get nicer upper bounds. So for n not equal to n tilde, we still have that n is congruent to n tilde mod d, and for that reason fn tilde minus fn is divisible by d. And if we cancel out the factor of d in the top and the factor of d in the bottom, we see now that the d is actually gone. So because we applied the Cauchy-Schwarz inequality and we got this copy of n, we have this difference fn tilde minus fn, which is divisible by d, and that's why this factor d here doesn't matter anymore. It cancels out with the top. So we have actually reduced the size of the modulus, and we hope that these off-diagonal terms now have better upper bounds than we would have had before with the larger modulus, m times d. And what we need to be careful about is not to make this diagonal term t to 1/2 times n to 1/2 too large. So it's expected that this expression increases with d and this one decreases with d. So one needs to be careful how big the size of the factor is one moves from the modulus. But this is the principle of the Q van der Corput method. And we now want to apply this to the problem of proving equidistribution estimates for smooth modeling. So if we So Polymath showed that, and this follows on from work of Zhang, Maynard, Dao, and so on. So Polymath showed that if we use the linear dispersion method, then and use completion of sums, then this statement here, which is a sum of the error terms for primes in arithmetic regressions, can be transformed into a question of bounding the following exponential sum. We have a sum over D, where D is a factor of the moduli Q, of the smooth moduli Q. We have a sum over N, where N is the support of some coefficient sequence. And then we have a sum over lambda, which comes from a completion of sums. And then we want to bound this exponential sum, which has phase b lambda over n plus cd. And in terms of the sizes or in the expression, involved in the expression, the factor d taken from the smooth modulus and used in the Q and the Corput method is allowed to be any size. So this is why it's important to talk about smooth moduli. If we have a smooth modulus, it has lots and lots of prime factors, and that means we can take out a factor of arbitrary size. And on the inside, the n in the critical range is x to 0.4, and the lambda depends on the exponent of distribution we want to prove. And the modulus md also depends on omega, and it decreases with as omega increases. So the larger the exponent of distribution is that we want to prove, the larger the modulus in the exponential sum is. And that lines up with what I said earlier, which is that it's harder to prove good upper bounds the larger the modulus is. So here is where the restriction on the omega will come in. So I'm going to talk about how to approach bounding this exponential sum in two ways. So I'm first going to talk about the approach of Polymath, and then I will talk about how we can change this a little bit to give a slightly improved result. So let's first talk about the approach of Polymath. So we have the sum over D, sum over N, and sum over lambda. And it kind of looks like something we can apply the Q van der Corput method to, except the problem is that we don't just have a sum over N on the inside, we also have a sum over lambda. So what we do is we simply take the sum over lambda and we move it all the way outside. So on the outside, we have a sum over lambda. And on the inside, we now have a sum over n. And that's exactly the situation for the Q van der Corput method I highlighted earlier. So what we do is we fix a residue class mod d and reduce the modulus from md to d. And then in order to get rid of the little d in the denominator, we apply the Cauchy-Schwarz inequality. And after applying the Cauchy-Schwarz inequality, we have this expression here. So on the outside, we have d squared times lambda to 1/2. And on the inside, we have a sum of em b lambda n tilde minus n over some denominator. And again, we see we are in trouble if the n tilde is equal to n, because then we get a 0 here and lots of 1s, and that's our diagonal term. So from this, from the case n tilde equals n, we get a diagonal term of d to 3/2 n to 1/2 times lambda. And then we still need to bound the off-diagonal terms. And to bound the off-diagonal terms, we notice that we can write n tilde is equal to, so because n is congruent to n tilde mod d, we can write the n tilde as n plus k times t. So replacing n tilde by n plus k times t, we get here n plus kt minus n, which is just kt, and then over t canceling out, we get b lambda k over n times n plus kt. And it turns out that very difficult result of the Lean's work on the Riemann hypothesis over finite fields can be used to prove upper bounds on this exponential sum over d and n. So we're viewing this as a sum in two variables. And using the Lean's work, one can prove an upper bound of n over m to 2/3 over t to 1/2 on that. So we have bounded the off-diagonal term and the diagonal term. And overall, what we need to show is an upper bound of dn. So if we want to make the diagonal term less than dn, then that means we need to make sure that the d is no larger than n over lambda squared. So the diagonal terms tell us that d can be no larger than n over lambda squared. And the off-diagonal terms become smaller as d becomes larger. So we take d as large as the diagonal terms allow. And that gives us, we know that n is x to 0.4. We now have an expression for d, and that means the only thing that's still flexible is the value of m. And so overall, if we want to make the n times m to the fourth, n times m to the third over t to 1/2 times t lambda less than tn, then that means we need to make the omega sufficiently small. And given the value of d we computed, we find that omega can be no larger than 7 over 600. So the restriction to getting better equidistribution estimates, so larger exponents of distributions, is that the diagonal term in the argument of Polymath can be no larger than n over lambda squared. And if we want to improve this, we would like to have a better value for the d. We would like to have smaller diagonal terms so that we can make the d larger. And if we can make the d larger, we get a better bouncing the off diagonal terms, and then we can choose a larger exponent of distribution. So the argument to making a smaller diagonal term is as follows. So in the Q van der Corput method application of Polymath, we had the sum over t, sum over n, and sum over lambda. And in order to apply the Q van der Corput method, we just took the sum over lambda and we moved it outside the sum. And then we just bounded it trivially. We didn't use any cancellation over lambda. The lambda was just gone. So we lost something there. So the idea to get an improvement is to get the lambda involved somehow. And the idea in the first step in the Q van der Corput method was always to fix the phase mod d. And we did this by fixing lambda and fixing n mod d. But we could also do this by just fixing lambda over n mod d. And that way the lambda stays involved. So this is the main idea. Instead of bounding lambda trivially, we look at lambda and n together and look at the ratio lambda over n and fixing its value mod d. And with that, we can again reduce the modulus here from md to m, apply the Cauchy-Schwarz inequality, and then after applying the Cauchy-Schwarz inequality, our exponential sum now looks different. So let me remind you, before it looked like this. It had b lambda n tilde minus n over something. And now it's much more complicated. It's b lambda n tilde minus lambda tilde n plus c lambda minus lambda tilde times d. So that means our phase now looks quite different and we have different diagonal terms. To be precise, if we say that c is 0, then our diagonal terms would be, for example, lambda n tilde minus lambda tilde n. So we would fix lambda, we would fix n tilde, and then that would determine everything else. And so instead of having just fixed n tilde, we also fix a lambda tilde, and so we get a different diagonal term. Before we had a diagonal term of d to the 3/2 n to the 1/2 times lambda, and now we instead have a diagonal term of t to the 3/2 n to the 1/2 times lambda to the 1/2. And here before that meant that in order to get an appropriate upper bound of dn, we needed d to be no larger than n over lambda squared. And now we need d to be no larger than n over lambda. So we are allowed to take a larger choice of d. Unfortunately, it's not that much larger because lambda is not that big. But by this argument of getting both n and lambda involved into the Q van der Corput method, we were able to get different diagonal term, which made the d a little bit bigger. And because the d is now a little bit bigger, that means we get a bit better bounds on the off diagonal terms, and that's what improves the exponent of distribution from 1/2 plus 1 over 40, 1/2 plus 7 over 300 to 1/2 plus 1 over 40. Okay, I think I have a bit time left to talk about this argument in a little bit more detail. And for demonstrative purposes, instead of talking about a general value of c, which makes this look quite complicated, I'm just going to assume for now that c equals 0. It's not 0 in the actual proof, but just to make it a bit clear, I'm just going to assume that c is 0. So if we assume that c is 0, what we wanted to do is to expound the expression b lambda over n by d times m. And after applying the Q van der Corput method, the alternative argument, we get b lambda n tilde minus lambda tilde n over d times n tilde. And clearly, something is a diagonal term if lambda n tilde minus lambda tilde n is equal to 0. And so we get that it's equal to 0 if we fix lambda and fix n tilde. And then we only get x to the epsilon choices for lambda tilde and n because it has only x to the epsilon divisors. And so that means we have lambda choices here, n choices here, d choices here, and then an extra x to the epsilon, which gives the before mentioned diagonal term t to the 3 half n to 1 half times lambda to 1 half. Okay, so this is the diagonal term. And then we still need to deal with the off-diagonal terms somehow. And for the off-diagonal terms, we use a similar argument to before. So before we started off with the condition n tilde is congruent to n mod d. And what we did is we wrote n tilde as n plus k times d. And that will replace the difference n tilde minus n by k times d. So this time, we have lambda n tilde is congruent to lambda tilde n mod d. And so that means that we have that lambda n tilde minus lambda tilde n is kd. And so we get to again have a k here and cancel d and d. And so the d is gone, which was the point of the Q van de Quaver method. The small issue is that we get an extra divisibility condition. So it's actually the case that n tilde is lambda tilde n plus kd over lambda. So we need to insist that lambda divides lambda tilde n plus kd. And that's just a small snug that can be that can be fixed by reparametrizing n, changing the summation a little bit. But overall, if we make this change, we have bk over n times lambda tilde over lambda n plus kd over lambda. And that looks really similar to the exponential sums we had earlier in the argument of Polymath. So in the argument of Polymath, they look just a little bit cleaner like that. But it turns out we can rearrange it to use the same Deline's bounds the Polymath had. We are in a slightly different regime. So in this different regime, Deline's bounds give instead an upper bound of lambda to 3 n over d. And we know that n is x to 0.4, and we know what lambda is. And the diagonal terms gave us a bound of t. So plugging all of this in, everything is known except for m. And so if we want to make this less than n times d and just rearrange a little bit, that's what gives us omega equal to 1 over 80. Okay, so I think I was talking a little bit too fast. So this is actually all I already had to say. But maybe if people have some questions.